So today is all about maximizing conic areas. So we're going to be using a graphing calculator in order to do that. The steps that I'm going to be following on the graphing calculator are on the screen right now. What I'll do is I'll make a separate video that shows me using the graphing calculator in order to find the values that I'm looking for. So I'm going to do all of the math on this video, and then I'll do the calculator instructions on a separate one. So if we take a look at that handout, we've got our first example here, and it says this. A rectangle is inscribed in an ellipse that has the equation 9x squared plus 4y squared is equal to 36. The sides of the rectangle are parallel to the coordinate axes. We want to graph the ellipse and an inscribed rectangle. Then we'll find the area of the rectangle in terms of a variable point xy, where one of its corners touches the ellipse. Then we'll plot the graph of the area, and then we'll do some more pieces of that problem as well. So let's do this first. Let's think about what this is asking us to do. We did something similar to this last semester where we maximized area under parabolas. So this is just kind of taking that one step further. I'm going to write this out first. We have 9x squared plus 4y squared is equal to 36. That's the equation of our ellipse. What I want to do is I want to get that into magnification form so that I can actually see what's going on and graph it. So in order to do that, I need the right side to be 1, which means I'm going to divide everything by 36. And what's left here is x squared over 2 squared plus y squared over 3 squared. That's equal to 1. That is the equation of our ellipse. So now let's graph that. That is an ellipse that has a center 0, 0, and a major and minor axes of the different lengths that we have here. So if I sketch this, I think I'm going to count by 2 along each axis. Is that going to fit if I do? Okay, center at 0, 0. We're going to go left and right 2 units. Because 2 is under the x value here. And then we're going to go up and down 3 units. Because 3 is under the y value. Okay, so along the y-axis, we move up and down 3 from the center. And then along the x-axis, we move left and right 2 because of our equation and the information that we were given there. Okay, sketch the ellipse. Looks something like this. All right, that is our ellipse. And then we're told that the sides of the rectangle are parallel to the coordinate axes. That means the rectangle sides are parallel to the x and the y axes. So let's just sketch a rectangle inside of this ellipse whose sides are parallel to the x and y axes. Looks something like that. All right, that is one option for a rectangle. Remember that there are many options out there. I'll draw some more in a minute after we've got the answers here. All right, last thing is this. We are going to call a point where the ellipse and the rectangle are touching each other, x, y. So I'm going to pick a point in the first quadrant. I'm going to call the point where the rectangle and the ellipse are touching each other, x and y. Now, in order for that to be true, that means we moved right x and we moved up y to get to that point xy. That'll become useful in just a minute. All right, we graph the ellipse and the inscribed triangle using that information that we have, so we did that. Let's find the area of the rectangle in terms of a variable point xy. So area of a rectangle, always base times height. Now, what do we know? In terms of the variables x and y, the base of that rectangle then is 2x. The height of that rectangle is 2y. So the area in terms of the variables x and y is 4xy. All right, unfortunately for us, we cannot type that into the calculator as is. The graphing calculators only take one variable, which means that I've got to get a way to get rid of the y. We need to find a way to write y in terms of x. So we've got an equation. That was the equation of that ellipse. 9x squared plus 4y squared is equal to 36. This is the equation that is going to allow us to get y in terms of x, and then be able to replace the variable. Okay, so I want to get y by itself. That is my goal with the equation for the ellipse. First thing I'm going to do is I'm going to subtract 9x squared from both sides. And then I'm going to get y squared by itself by dividing by 4. So this is y squared is equal to 36 minus 9x squared over 4. All right, last thing we're going to do is we're going to take the square root of all of that. And I'm going to plug that value in for y. Now, there's a way to simplify this. You can if you'd like. I don't care if you leave it like that though, because we're just going to be plugging things into our calculator later. So that's fine if you want to go only that far. But everywhere I see y in the equation for area, I'm going to replace it with that whole square root. So the area now, just in terms of the variable x, is equal to 4x times the square root of 36 minus 9x squared all over 4. Remember that 4 in the denominator there is part of the square root. All right, so that is the equation for the area of the rectangle in terms of x and also in terms of y. Okay, now we're going to plot the graph of the area as a function of x. So I'm going to do that in my graphing calculator, and I'll be right back. Okay, so we're back. What I did is I graphed that equation for area in terms of x in my graphing calculator, and then I just sketched a really rough curve of that in the bottom right hand corner of your screen, and then I calculated the maximum of that curve using my graphing calculator again. I'll put a video up of how I did that, but that will be separate. Okay, what this graph represents on the y-axis are all of the possible areas that we could inscribe a rectangle in that ellipse. So if you take a look at the diagram right above of the ellipse that we had graphed, there are other options for rectangles. I could have drawn a rectangle that was taller and skinnier. I could have drawn a rectangle that was shorter and wider. I could have drawn a rectangle that was like super tall and really skinny. Okay, we have many, many options for rectangles inscribed inside of this ellipse. What the area equation does for us is it allows us to calculate all of those possible areas of any rectangle that we can inscribe in that ellipse. And then by finding the max, we find the max possible area that we can get if we take a rectangle and stick it inside that ellipse that we graphed above. So our maximum area possible is 12. Can't go any bigger than that. That was the maximum area. Now remember that we defined the base of this rectangle as 2 times that value of x. Now when we found the maximum area, the x value was 1.41. So 2 times 1.41, that is going to be the base of the triangle that has a maximum area. So our base here is about 2.82. So a rectangle with a base of roughly 2.82 has the maximum area that we can inscribe in this ellipse. Now let me graph it and see what that looks like. Just roughly sketching that. 2.82. It's almost actually exactly what we had graphed before. Just a tiny bit skinnier there on the inside. All right, that would be the rectangle with that maximum area. All right, so let's answer the next questions regarding this information. Next question. Okay, next question then. What is the length of the base of the rectangle with the maximum area? Well, we just did those calculations right above. So the base we defined as being 2 times x. So we have 2 times 1.41. The base is about 2.82 units. Okay, what is the height of the rectangle with the maximum area? So how did we define the height? Well, we defined the height as 2 times y. So there's a couple of things that we can do. We had an equation for y. We said y was equal to the square root of 36 minus 9x squared over 4. That's how we defined y right above. So we can find y by just plugging that into this equation and evaluating. Because we have x, we don't have y. We know x is 1.41. Okay, when I plug all of that in, when I replace x with 1.41, I'm just going to do this in the calculator. We get something, let's see, that is about 4.24 units. Okay, another option we could have gone with there. Remember that area of the rectangle was base times height. Now, what did we know about that rectangle? Well, the rectangle had a maximum area of 12, and its base we found above was 2.83. So we could just find the height by taking 12 and dividing by 2.83 as well. You should get the same answer there, about 4.24. So it doesn't matter how you choose to do it, but that is how we're going to do this one maximization problem. Okay, second video will be the second example.